Okay, so today what we're going to do is we're going to talk about 3.1.2. How, again, can I represent it? This time we're going to use a tree diagram. So in the previous lesson, we used an area model to represent probability situations where some outcomes in the sample space were more likely to happen more than others. Today we're going to consider how to represent these types using a tree diagram. So it's just a different way to do this. So let's look at our first question, shall we? So, question number 12. Your teacher challenges you to a spinner game. You spin the two spinners with the probabilities listed at the right. The first letter comes from spinner 1 and the second letter from spinner 2. If the letters can form a two-letter English word, you win. Otherwise, your teacher wins. So what I want you to do is I want you to pause the video and you're going to go ahead and figure out what the outcomes are, look at these three questions, and ultimately decide, is this game fair? So pause video now. Okay, so let's talk about these three questions. So the first question says, are the outcomes for spinner 2 independent of the outcomes of spinner 1? So that means if I spin this spinner, it's not going to affect this spinner. So are they independent? Absolutely. So yes. Okay, so now what we want to do is we want to make an area model of the sample space and then calculate the probability that you will win this game. So this time we did not make an area model for you. So let's go ahead and draw an area model. I can't see my area model yet. Cool. So I'm going to say spinner 2 right here, and I'm going to say spinner 1 right here. All right. So if we take a look at so let's look at spinner 2 for a moment. So here is spinner 2. Notice that this is a 90-degree angle, right? So if I cut this circle, I should say, into 4 equal parts, right? Each part will have a 90 degrees. So I can say confidently that this is 1/4, and the rest of all of this space, all this leftover space, is going to be 3/4. So when I make my area model, right, I have two letters I'll get, T and F. So I'm going to say the probability for T, that's a 1/4, right? And the probability to get an F is 3/4. Right? So you cut that up. Okay. So let's take a look at spinner 1. So half of the model is with I. So we can go ahead and we can say what I is. Now we got to figure out what A and U is. So we want to take that degree right there. That's 60 degree. That's going to help us. So a whole circle is 360. So if I take 60 and divide it by 360, right? First the zeros cancel out. So you have 6/36, which ultimately will give you 1/6. So the probability to get the letter U is a 1. Your A is a 1/3 chance. And that leaves I, and I, we said originally was a 1/2. So I, 1/2. So if you multiply your fractions together, this will be 1/24. This will be 3/24. Leave them all as the fractions. If you want to simplify them, that's fine. But we can, if you leave them all as 24, we can actually add them up, and you can easily remember that they all add up to the number 1. So this will be 1/12, or aka 2/24. This will be 3/12, or 6/24, and 1/8, so 3/24. And then this will be, what, 3/8, which again will be 9/24, and we can add them all up. So that's our probability spinner, or model, I should say. So we want to calculate the probability that you will win the game. So let's think of some letters that you have to be able to spin. So your teacher will only win if it's a 2-letter English word. So the only letters I can think of that give you a 2-letter is the word if, the word it, and the word at. So if you spin a U, you are out of luck, right? So let's figure out what the probability to spin the IF, right? So that means I am going to spin an I and an F. So where is my IF? Yeah. So it's right here. So I and then F, 3 over 8. My P of IT. So here's my I, here's my T. Probabilities 1 over 8. And then last but not least, I said at. So here's my A, and here's my T. So the probability of at is 1 over 12. So what we want to do is we want to add these numbers up to figure out what our total probability is. Now notice they don't have the same denominator, so we're going to have to make them all be the same denominator. So 3 over 8, I'll multiply it by 3 over 3, which gives me 9 over 24. And then 1 over 8, multiply it by 3 over 3, which gives me 3 over 24. And then I'll multiply 1 over 12 by 2 over 2, which is 2 over 24. So let's add up those numbers. So I'll do it over here. So 9 over 24 plus 2 over 24 plus 3 over 24. So 9 plus 2 is 11. 11 plus 3 is 14 over 24. And 14 over 24 we can simplify that. Let's go ahead and simplify that. So 2 goes into both. So that simplifies down to 7 over 12. That is the probability to getting a word that works. So now that we found the probability of winning this game, let's go and ask, is this game fair, right? Would you actually want to play this game 100 times, okay? So that's what this last question is. If you played it 100 times, who do you think would win more often, you or your teacher? How can you make sure that this will happen? So no, this game is not fair whatsoever. You would expect to win more often than the teacher if you played 100 times, because if you take a calculator and you divide 7 and 12, you are going to get the decimal 0.583 repeating, which is 58.3%. So you are going to win 58 out of 100 times against your teacher, which means that you would win all the time. You'd want to play. Your teacher would not want to play. That's all that this question is asking you to do. All right. So let's continue. Let's flip it over to the next question. Question number 13. So Sinclair drew a tree diagram at the right to model the spinner game from the last question. Sabrina says, well, that can't be right. The diagram makes it look like all the words are equally likely. So look at the one on the right, right? And I blew it up a little bit for you guys so you guys can actually see it. So if we look at this one, it does look like it's equally, it looks pretty equal. The spinners are not equally divided. Yes, they have, you see the I, the U, the A. The I has the T and the F. The U has the T and F. The A has the T and F. But they don't have their probabilities yet. So what we want to do is we want to write those probabilities in, right? So if we go back to this question, it says, to make this tree diagram reflect the true probabilities in this game, Sabrina writes the numbers on each branch showing the probability. So she writes a 1/3 on the branch for A, a 1/4 on the branch for T. So what she's doing is she's doing this. So we said that the I, or not the I, the A has a probability of 1/3. So she wrote a 1/3 on this branch, right? She said the probability for T, for that branch, is a 1/4, right? Now, the T has multiple branches. It has a 1/4 branch here. It has a 1/4 branch here. So that's all she's meaning, right? So you can fill in the chart with what we know. The U had a 1 in 6. The I had a 1 in half. What did the T have? So 3/4, or sorry, the F, I should say, 3/4 and 3/4. So that's all we're doing is we're filling in that chart. Okay? So it's a different way to represent all this stuff. So according to this probability area model that you made in this last question, what was the probability that you rolled, or I should say, excuse me, spun to get the word at, right? Now we want to examine in the branch on this tree. So if I go back to my original at problem, I said the probability to get the AT was a 1 in 12 chance, right? So now looking at this branch, okay, we want to be able to get the same answer. So if I start my spinner here and I'm going to go on that branch, I see the 1/3, and to get to the T, it's a 1/4. So to get this outcome of at, I'm going to take the 1/3, I'm going to take the 1/4, so I'm multiplying my branches together, and I get a 1/12. So that's all that's saying, is that you can multiply your branches together, and you're going to get the same exact two-letter combination. So let's go ahead and show you for the rest. So 1/3 times 3/4, right? The 3's will cancel out eventually, but for our sake of argument, let's just leave it as 3/12 because that was what we had in our box originally. This will be 1/6 times 3/4, so this was 3/24. This is 1/6 times 1/4, so 1/24. 1/2 times 1/4, because again, here's the 1/2. So this will be 1/8, and 1/2 times 3/4 is 3/8. So these numbers are the same numbers that we've seen in our area model. So this is just another way to get our data. That's all that's saying, right? So just verify that these numbers represent those numbers here. Okay? Fantastic. So now let's see if we can take this information and put it in a different problem. Okay? The famous rat race. Okay? So, this rat race. So Ryan has a pet rat, Romeo, that he boasts is the smartest rat in the country. Well, Sammy overheard Ryan at the county fair claiming that Romeo can learn to run a particular maze and find the cheese at the end. I don't think Romeo is that smart, Sammy declares. I think the rat just chooses a random path through the maze. So Ryan has built a maze with the floor plan shown at the right. In addition, he has placed some cheese in an airtight container, so Romeo cannot smell the cheese in room A. So what we want to do is we want to build some branches. So what we learned about in the last problem, I want you to see if you can try to figure out what we can do. Right now, we know that everything is equal, and I'm going to blow this up so we can see it a little bit bigger. So this means that here's Romeo the rat, right? He has 1, 2, 3 options to go down. So that means he has a 1 1/3 to go this way, a 1 1/3 to go this way, and a 1 1/3 to go this way. Each time you come to kind of a fork in the road, right? You're going to count how many forks in the road you have, right? And it'll be 1 out of that number, right? So if I travel down this road, here's my fork in the road, I have a 1 in 2 chance of going either direction. So this will be a 1/2, and that'll be a 1/2. This one, fork in the road, there is no fork, I end up in the A. Here, the fork in the road, there's 3 chances. So this will be the 1/3, this will be a 1/3, and this will also be a 1/3. Okay? So go ahead, now that we've kind of filled this out, go ahead and pause the video and try to answer the remaining questions about Romeo and this awesome rat. Okay, so let's come back. Let's actually talk about and answer these lovely questions. All right. So suppose that every time Romeo reaches a split in the maze, he equally likes to choose the paths, choose a method, calculate it, and in a sentence or two, explain why you chose the method you did. right? So essentially what you're saying is that if I wanted to get to a certain path, right? If I go this way and this way, right? This is a 1 in 9 chance of getting to room B. 1/3 times 1/3, again, 1 in 9 chance getting to room B. This is a 1 in 9 chance of getting to room A. This just stays as 1/3. This one, though, is 1/3 times 1/2. So this will be a 1 in 6 chance. And then this way is a 1 in 6 chance getting to room B, right? So what we want to do is we want to choose a method and calculate the probability that Romeo will end up in each room, right? So we'll say room A, right? Probability. So that means the probability for A is everything that leads to A. So this would be this probability right here. So that would be a 1 in 9 chance. This probability right here. So this will be a 1/3 chance. And then finally, this probability right here, which will be a 1 in 6 chance. 9, 3, and 6, they all have a common denominator of 18. So 2 over 2, 6 over 6, 3 over 3. So 2 times 1 is just 2. 6 times 1 is just 6. 3 times 1 is just 3. So if I add up all of these numbers, I get 11 over 18. So the probability, if we divide 11 over 18, should be about 0.61 with a bar repeating it. So we could just say 61%. Okay. And then let's do room B. So the probability of room B is everything else. So that'll be the 1/9. So 1/9, the second 1/9, and finally the 1/6. So again, they all have a common denominator of 18. So 2 over 2, 2 over 2, 3 over 3. So 2 times 1 is 2. 1 times 2 is still 2. 3 times 1 is 3. So 4 plus 3 gives you 7 over 18. So 7 over 18 is about 0.38 with a bar over it. So about 38%. Well, actually, let's round up since it's 0.38. So let's say 39%. And we're going to do that also because if you add 39 with 61, you're going to get 100%. We want to make sure that we get 100%. Okay? So if the rat moves, has 100 attempts, how many times would you expect Romeo to end up in that room? In room A, you'd expect about 61 times. In B, you'd expect about 39 times, right? Why? Because it's 61%, so we could say that that's 61 out of 100 times, 39%, right? Because it's 39 out of 100, right? So after 100 attempts, Romeo has found the cheese 66 times. See how smart Romeo is, Ryan asks. He clearly learned something and got better at the maze as he went along. Sammy isn't so sure, right? So do you think Romeo learned and improved his ability to return to the same room over time? Or could he just have been moving randomly, right? We want to make sure that we can write an argument to either convince either the Sammy character or the Ryan character to feel like he was right. So again, there might not be an exact correct answer. So while Romeo's results are better than expected, right, because he can do it 61 times, 66 is not really that much better than 61. So as long as you have a really good argument, either one is good. So let's continue with Sammy the rat, and sounds like an old time Sammy the rat. Sorry, got distracted. All right, so always skeptical. Sammy says, if Romeo really can learn, he ought to be able to figure out how to run this new maze that I've designed. So let's examine the maze at the right. So to give Romeo the best chance at finding the cheese, in which room should the cheese be placed? So I want you to choose a method, show all your steps. So we've done this problem together. Or we've done a couple problems together, and then try to answer if the cheese is in room C and Romeo finds the cheese 6 out of 10 tries, does he seem to be learning? So go ahead and answer those questions. Pause the video, and that's it. Okay, so let's first build our rat race. And so I have a blown up picture right over here. So here's my rat coming through. I have two options. So this will be a 1/2 and 1/2. I travel down this road. I have a 1/3 chance for all of these. Right? Excuse me. Travel down this road. I have a 1/2 chance going here. So 1/2 and 1/2. I end up in room C. Here, though, I have two more chances of either end up in B or C. So let's go ahead and multiply. So 1/2 times 1/3. So this one would be a 1 in 6. This one would also be a 1 in 6. This one would also be a 1 in 6. Down at the bottom, so 1/2 times 1/2. This would be a 1/4 chance. 1/2 times 1/2 times 1/2. So that is going to be 1/4 times 1/2. So this should be a 1/8 chance. And then 1/2 times 1/2 times 1/2 will also be a 1/8 chance. So the probability, if the cheese is in A, there's only two things that'll come up. So it'll be a 1/6 plus 1/6, which gives you 2/6, which simplifies down to 1/3. So that's roughly 0.3 with a bar over it. So 33.3%, we can say. Probability for if the cheese is in the B room. This will be a 1 in 6 plus a 1 and 8. Not the same denominator. Common denominator is 24. So 4 and 4, 3 and 3. So this will be 7 over 24. Again, in your calculator, 7 over 24 is about, I think, 0.29, 0.2916, right? So that means it's 29 let's just say 2%. And then probability for C is the bottom. So this will be 1/8 plus 1/4. Common denominator is 8. So this will be a 3/8, which is 0.375. So this will be 37.5%. Cool? Great. So there is our percentages for this one. So in order to give him the best probability, which room should we put the cheese in? It should be this room, C, because it has the biggest probability, right? It should not be B. It's 29.2%. A is pretty close with 33.3, but again, C is the best room. Okay, so last but not least, the last question, it says, if the cheese is in room C and Romeo finds the cheese 6 out of 10 times, does he seem to be learning? So again, 6 out of 10 is about 60% of the time. So Romeo's results are much better. Are much better than the expectation in this case, that it seems really unlikely that this rat is getting lucky, right? Because he has a 37% chance of getting lucky. So if he gets it 60% of the time, that's really good. He's probably learning that where the cheese is. Okay, so that's all about probability and so tree probability. So if you have any questions, let us know. The homework is going to be problems 6 through 11 and 17 to 22.